Hello friends. In the last lecture, we have discussed how to form a partial differential equation by the elimination of arbitrary function and two examples which are based on it. Before it, we have studied how to form a partial differential equation by the elimination of arbitrary constants and the examples which are based on it. Now in today's lecture, we will discuss the rest of the examples which are based on how to form a partial differential equation by the elimination of arbitrary function. So what is given third example, C friends, form a partial differential equation by eliminating the function f from z equal to x to the power n into f of y upon x. So if you observe here, friends, here function f is given, and our target is to eliminate that function f from this relation. So we will apply the method. We will first consider this given relation as it is, z equal to x raised to n into f of y upon x. And then, friends, what we have to do, suppose it to be equation 1. Differentiate this equation partially with respect to x and partially with respect to y. So while differentiating this partially with respect to x or partially with respect to y, particularly partially with respect to x, if you observe the right hand side, x is present here in x raised to n, as well as x is present in this function f of y upon x. So while differentiating this partially with respect to x, we have to use the product rule on the right hand side. So LHS you will get dabba z by dabba x, because z is a function of two independent variables x and y. So there you will get LHS dabba z by dabba x is equal to, on the right hand side you use product rule. X raised to n first function remains as it is, into derivative of f of y upon x with respect to x, you will get f dash of y upon x into derivative of the function y upon x, or the quantity which is present in this bracket, that is y upon x, partially with respect to x, keeping y constant, you will get it as minus y upon x square, and that term is written here. Dabba z by dabba x is equal to x raised to n first function as it is. Derivative of f of y upon x with respect to x, it gives f dash of y upon x into derivative of this bracketed function partially with respect to x. You will get it to be derivative y is a constant, and derivative of 1 upon x with respect to x, you will get it to be minus 1 upon x square. So this gives the first term. What is second term? The function f of y upon x remains as it is. That is second function as it is, into derivative of first function, that is x raised to n with respect to x. You will get n x raised to n minus 1. n x raised to n minus 1. And if we differentiate equation 1 partially with respect to y, LHS it gives it to be dabba z by dabba y. LHS it gives dabba z by dabba y is equal to, while differentiating z partially with respect to y, you keep x as constant. So x raised to n remains constant there, into derivative of f of y upon x with respect to y, you will get f dash of y upon x into derivative of this y upon x with respect to y, keeping x as constant, means 1 upon x remains as it is, into derivative of y with respect to y, you will get it to be 1. Means it gives dabba z by dabba y equal to what it gives, x raised to n into f dash of y upon x into 1 upon x. So if you observe here, this term and this term present here as well as here. But when you will get these two terms to be same, because here we have negative sign, here we have positive sign. If you multiply this by x and if you multiply this equation 3 by y, then you will get this term and this term to be same with opposite signs. So if you have taken the addition, this term gets cancelled from equation 3 and from equation 2. So what you have to do, friends, you multiply this equation 2 by x and this equation 3 by y, and take the addition. So LHS it takes x dabba z by dabba x plus y dabba z by dabba y is equal to, if you multiply this first term by x, what it gives, you see here x is to n divided by x square is there already, means there you will get x is to n minus 2 by using laws of indices, and if you again multiply it by x, there you will get by again laws of indices x is to n minus 2 into x, means x is to n minus 2 plus 1, and there you will get x is to n minus 2 plus 1 means x is to n minus 1, and that is written here. This negative sign is taken here. This y is as it is here into f dash of y upon x is as it is. Plus, if you multiply this term by x, then n f of y upon x remains as it is. That is here n f of y upon x. And if you multiply this by x, there again by using laws of indices, it gives x is to n minus 1 into x, means it gives x is to n minus 1 plus 1, means there you will get x is to n. And if you multiply this by y, there you will get y f dash of y upon x as it is, y f dash of y upon x, and here x is to n upon x, there you will get x to the power n minus 1. So friends, what happens? This term and this term both are same and having opposite signs. So this first term and this third term gets cancelled. And what is left here? N x is to n f of y upon x. But friends, by the help of equation 1, x is to n f of y upon x is nothing but z. X is to n f of y upon x is nothing but z. So you substitute its value there. So here you will get the right hand side to be n into z. So we have obtained here the equation. In that equation, f is not present there, means we have eliminated f, means this obtained equation is what we call it as a required partial differential equation by the elimination of the arbitrary function f from it. And friends, if you know, in the last semester, uh, we have studied here this statement as a statement of Euler's theorem. Statement of Euler's theorem: x dabba z by dabba x plus y dabba z by dabba y is equal to nz. So that statement is not new for you, but here by the elimination of that function f, we have what that form the partial differential equation x dabba z by dabba x plus y dabba z by dabba y equal to nz. Now, what is another question given, friends, here? Another question given here. Eliminate arbitrary functions small f and capital F from y equal to small f of x minus 80 plus capital F of x plus 80. So, friends, you remember here LHS is a y and right hand side is in terms of x and t. So, you remember here dependent variable is y and independent variables are x and t. Means to form here the partial differential equation by the elimination of small f and capital F, you differentiate y with respect to small x and y with respect to small t. So remember one thing in your mind, here y is a dependent variable and which depends upon x and t. So that's why while differentiating with respect to x, y is not constant, but it is a function of x and t. And similarly, while differentiating with respect to t, again it is not constant, but it is a function of t. So while differentiating y with respect to x, you treat t as constant, and while differentiating y with respect to t, you treat x as constant, or you keep x as constant. So first we will consider this given relation as it is: y equal to f of x minus 80 plus capital F of x plus 80. Now what you have to do, you differentiate this y with respect to x. So LHS it gives dabba y by dabba x is equal to derivative of this first term partially with respect to x, keeping t as constant. There you will get f dash of x minus 80 into derivative of this bracket with respect to x, keeping t as constant, you will get it to be 1, and that is not written here, plus Derivative of here this second term, you will get capital F dash of x plus at into derivative of this bracketed function with respect to x, keeping t as constant, you will get it to be 1. So delta y by delta x, you will get it to be f dash of x minus at plus capital F dash of x plus at. Now what you have to do? Again you differentiate this with respect to x. So if you again differentiate it with respect to x, it gives what? Delta 2y by delta x square is equal to derivative of f dash of x minus at with respect to x, it gives f double dash of x minus at into derivative of x minus at with respect to x is 1, no need to write here, plus derivative of capital F dash of x plus at with respect to x, you will get capital F double dash of x plus at into derivative of x plus at with respect to x is 1. No need to write there. Means it gives delta 2y by delta x square is equal to what? Small f double dash of x minus at plus capital F double dash of x plus at. Now what you have to do, you differentiate one partially with respect to t, we get, if you differentiate one partially with respect to t, we get LHS, it gives delta y by delta t because y is a function of t also. So LHS will get delta y by delta t is equal to derivative of f of x minus at with respect to t, you will get f dash of x minus at into derivative of x minus at with respect to t, keeping x as constant, you will get it as a minus a. X is constant means derivative of this term is 0, and derivative of this term with respect to t minus a is constant into derivative of t with respect to t is 1, plus derivative of f of capital F of x plus at with respect to t, you will get capital F dash of x plus at into derivative of x plus at with respect to small t, keeping x as constant, you will get it to be a. Again, if you differentiate this relation partially with respect to instead of x, this must be t prime. So you note this change in your notes. Instead of x, this must be t. So differentiate this relation again with respect partially with respect to t, we get LHS, it gives delta 2y by delta t square is equal to this minus a remains as it is there. Derivative of this you will get f double dash of x minus at into derivative of x minus at partially with respect to t, you will get it to be minus a. That minus a and this minus a, you will get it to be plus a square. Means derivative of this first term you will get f double dash of x minus at into there you will get a square plus derivative of this function again with respect to t, you will get it to be capital F double dash of x plus at into derivative of x plus at with respect to t, partially with respect to t, you will get it to be a. That a and this a, there you will get a square. And if you observe here this right hand side, you will get a square as a common. So you take it as a common. So if you have taken a square as common, what is left here in the bracket? F double dash of x minus at plus capital F double dash of x plus at. But by the help of equation 2, if you observe small f double dash of x minus at plus capital F double dash of x plus at, value of this expression is delta 2y by delta x square. So you substitute value of this bracket from equation 2 as delta 2y by delta x square. So if you observe here this equation, this is free from small f and capital F. Means, and it only involves what? Partial derivatives. So this is nothing but what we call it as a required partial differential equation, which we obtained by the elimination of the arbitrary functions small f and capital F from the given relation. So in my sense, if you understand here the solutions of both explained problems, now I will proceed towards the next example. So what is next problem, friends? Home partial differential equation by eliminating the function small f from z equal to e to the power ax plus by into f of ax minus by. So here f is present here, and our task is to eliminate that function so that we get the partial differential equation. So friends, what we have to do here? Here again you consider the given relation as it is. That is given z equal to e to the power ax plus by into f of ax minus by. And now friends, what you have to do, you differentiate this relation. Suppose it has a equation 1 and differentiate this partially with respect to x and y. So on LHS we have z, which is a dependent variable and which is a function of two independent variables x and y. Here a and b, these are constants. So what we have to do, while differentiating the z partially with respect to x, you keep y constant, and while differentiating the z partially with respect to y, you keep x as constant. But if you observe here this right hand side, then x is present in this exponential function as well as in this function f. Similarly, y is present in this exponential function as well as in this function f. So while differentiating right hand side partially with respect to x or partially with respect to y. Here x is present in both the functions, y is also present in both functions. So you have to use what? The product rule for the differentiation. So differentiating this one partially with respect to x and y, we get LHS, it gives dabas here by daba x is equal to, use here the product rule for the differentiation. First function as it is e to the power ax plus by as it is, into derivative of this function partially with respect to x. You will get f dash of ax minus by into derivative of ax minus by partially with respect to x keeping y constant. Means this term you will get constant, its derivative is 0, and derivative of this term partially with respect to x you will get it to be a. Means you will get first into derivative of second as e to the power ax plus by into f dash of ax minus by into a, plus this second function as it is, that is I have written here f of ax minus by, and we need to find the derivative of first function, that is e to the power ax plus by. So while differentiating or while taking the derivative of exponential function, its derivative we will get it to be exponential function as it is, means derivative of e to the power ax plus by, you will get e to the power ax plus by as it is into derivative of here this function which is in the power of e partially with respect to x. So that derivative partially with respect to x, keeping y constant, you will get derivative of ax with respect to x, you will get it to be a. That is written here. And this term is constant, its derivative is 0. Means you will get second term as second function into derivative of first. You will get second function as it is and derivative of first e to the power ax plus by into a. Similarly, friends, what we have to do? Similarly, if you differentiate this equation 1 partially with respect to y, LHS it gives dabba z by dabba y is equal to, again use here the product rule to find the derivative of this right hand side, e to the power ax plus by as it is, means first function as it is, into derivative of this second function with respect to y, keeping x as constant, you will get f dash of ax minus by into derivative of ax minus by with respect to y, keeping x as constant, you will get it to be minus b, plus this second function as it is, that is f of ax minus by into derivative of this first function partially with respect to y. You will get it as derivative of exponential function, you will get exponential function as it is, e to the power ax plus by into derivative of the function which is in the power of e partially with respect to y, keeping x as constant. He will get first term as constant, its derivative is 0, and derivative of by partially derivative of by with respect to y, you will get it as b. So if you observe friends, we have a here in this expression as well as in this expression. We have b here in this expression, but this having negative sign, this having positive sign. So if you multiply this by b and if you multiply this by a, and if you have taken the addition of these two terms, you will get these two terms gets cancelled to each other. And that's why what you have to do, you multiply this equation 2 by b and this equation 3 by a and take the addition. So there you will get LHS b dabba z by dabba x plus a dabba z by dabba y, that is written here, is equal to, if you multiply this by b, you will get ab e to the power ax plus by into a place of ax minus by. And if you multiply this by a, there you will get minus ab e to the power ax plus by into a place of ax minus by. Means the same term having opposite signs get cancelled. Plus, what you will get, multiply this by a, means there you will get ab e to the power ax plus by into f of ax minus by. And if you multiply this by a, there you will get ab e to the power ax plus by into f of ax minus by. Means we get the same term how many times? Two times. Means there you will get 2ab e to the power ax plus by into f of ax minus by. But friends, e to the power ax plus by into f of ax minus by the help of equation 1 is nothing but z. Means there you will get right hand side as, I forgot to write this ab here, friends, ab here. So 2 ab remains as it is, and value of this function e to the power ax plus by into f of ax minus by, you will get it to be what? Z. Means right hand side you will get 2ab into z. So you note this change, correction. Instead of only 2, we must have 2ab, and value of this function by the help of equation 1, you will get it to be z. So if you observe here this obtained equation, b dabba z by dabba x plus a dabba z by dabba y is equal to 2ab into z, which is free from f. Means this obtained equation is a partial differential equation which we obtained by eliminating the arbitrary function from this relation. So in my sense, if you understand here the solution of this problem also. Now friends, I have given here the two examples to you for homework. So what is given? Form a partial differential equation by eliminating the arbitrary functions f and z from z equal to y into f of x plus x into z of y. So you consider this relation as it is. Here z is a dependent variable, x and y are independent variables. Means while differentiating z partially with respect to x, you keep y constant, and while differentiating z partially with respect to y, you keep x constant. And straightforward you take the derivatives. Maybe you will need to find the second order derivatives similar to that example number 4, and easily you will get here the required here partial differential equation by the elimination of the arbitrary constants f and z. But you try it at home. If you are not getting the solution, you ask me at any time. Then what is another question given? Form a partial differential equation by eliminating the arbitrary function phi from phi of x square plus y square plus z square, comma z square minus 2xy. So friends, to solve here this example, either you have to use the method of example number 1 to form the partial differential equation, or you use the method of example number 2 to form the partial differential equation. So what is my advice to you? My advice to you is you use method of example number 2 to solve it. So what you have to do, you take here this first function. This relation is equal to u, and this relation is v. Means you take u equal to what? X square plus y square plus z square, and v equal to what? Z square minus 2xy. And then you will get this function as phi of u comma v. But the function phi of u comma v, we can write it as u equal to phi of v or v equal to phi of u. So you write it as, first you mention we have You write here this function as it is. We have given phi is equal to, or this function you consider as it is. Then below it you mention above function can be written as u equal to phi of v. U equal to phi of v. That is, what is u? U is nothing but x square plus y square plus z square is equal to phi of v, means there you will get phi of z square minus 2xy. And you will get here this example similar to example number 2. That is x square plus y square plus z square, or you mention given function phi can be written as x square plus y square plus z square is equal to pi of z square minus 2xy. You start your solution like this. Given function phi can also be written as x square plus y square plus z square is equal to pi of z square minus 2xy. And then you apply the method of example number 2 to form the partial differential equation. So if you have any doubt, or if you are not getting the solution of any example, then you ask me at any time. Now, our next article from the syllabus is what? Lagrange's linear equation. But friends, this is the last article from your syllabus, Lagrange's linear equation. But we'll discuss, friends, that part in the next lecture. So have a good day, friends. But you solve the problems, two problems, which I have already given for the homework. So have a good day.